Okay, so this is a continuation from the last lecture, last video, and so I'm going to go ahead and jump to where we left off, which is right here. Okay, so this is kind of a chunky example, but I think you'll see the what I'm trying to get at on this thing. So this is just a generic memory. What I've done here is I've given it some special control signals. What you can see on this thing, it is a bidirectional memory, and it should be tri-stated. I always forget to put that tri-state symbol in there. So it is tri-stated memory, which is what what the chip select is, or the output enable is selecting on this thing. So this is a chip select and the output enable, and it has a write enable. So this is write enable is just a normal write enable, but these are the two signals that are going to control the operation of this thing. So the write enable, once again, it allows the thing to be written, but the output enable essentially does two things. It drives the tri-states, and it essentially kind of the same thing, but it controls the direction of the data. So let's use this as an example. So our first example is taking this memory and extending the data width. So this is essentially, well, I call it the word length. Essentially what I have is a 256 by 8 RAM. I want to make it effectively into a 256 by 16 RAM. And it's very straightforward. I mean, I really don't do that much to it, except I connect the addresses together. So they share the same address space. That's the punchline is in this one. I'm extending the data space, and they're sharing the same address space. So the data now, it's 16 bits. I'm just saying the output of one of these RAMs happens to be, output of one of these RAMs is the lower 8 bits. The output of the other RAM is the other 8 bits. So the control signals for this, I don't really have to worry about too much. It's just all shorted together. And so this is one way to draw it. This is another way to draw it. Essentially, I've included the shared resource on this thing. So these are two 8-bit lines that are feeding a 16-bit line. There's absolutely no chance of bus contention on these things. Okay, so where it gets interesting is extending the address space. Okay, so the notion here is I have four of these devices right here. I want to tape them together and make a 32K by 16. And so what I need to do is essentially have some magic interface circuit here. And the issue with this interface circuit is what circuit do I use to interface these things? So the idea here is these four memories are going to be sharing this. They're going to be sharing this output, one 8-bit output. So the idea here is this circuit here has to make sure only one of these memories at a time is driving their data onto this shared resource here. So the magic circuit we're looking for is something hopefully you remember is a standard decoder. The notion of this this is a standard 2 to 4 decoder here. The notion is the way this circuit is set up is that only one of these outputs can possibly be on at any given time. So this, if you remember, this kicks out a one hot output, which is what we're looking for. We're looking for a circuit that turns one thing on and all the other things off. Standard decoder is perfect for it, and that was we didn't really use it too much in 133, but this is where it's used quite a bit in working with memory. So the problem now becomes it's different now. Instead of extending the data space, I'm extending the address space. So what I'm going to do is take two of these 256 by 8 RAMs and create a 512 by 8 RAM. Okay, so the notion is that the data is staying the same, but the address space is growing. So 256 by 8 has 8 address lines. What I'm going to need to do is get essentially another address line in here, and the standard decoder is going to help me do that. So here is the solution to this thing, and what I've done here is these two devices here, they still share the same 8-bit address lines, but what I'm going to do for that 9th address line, which I need to get to address 512 things, I am going to turn one of these RAMs off. Okay, so I'm going to turn it off by using a decoder. So the decoder, what's going to essentially turn these two devices on and off, is going to be driven by what I'm going to say is that 9th address bit. So if that 9th address bit is a 0, it turns this one on and this one off. If that 9th address bit is a 1, here's my 1, it turns this one on and this one off. Okay, so this is my magic circuit solution. I'm making this work. Certainly they do share the same other two control signals, but the chip select is driven by this decoder, which only selects one of these to be on at a time. Now the notion here is these two devices are connected to the same shared resource. I have to make sure I never have these devices driving both of their datas onto the bus at the same time. And the notion here is the decoder is perfect for that. So here's the associated memory map on this thing. Here's my 8 bits. So each of these are equivalent. There are 8 zeros through 8 ones. What makes them different is the fact that the decoder is kind of assigning 0 to this memory and assigning a 1 to this memory, which makes it which ensures that essentially both of these RAMs are not driving their data onto the bus simultaneously. Don't want bus contention on this. So that works great. We're going to transfer up to doing whatever we need to do on these things. And so this is a similar example is take 4 of these devices, 8K by 8, 13 address lines, and making it into a 32K by 8. And the way we're going to do it is essentially we need 2 address lines. We have 4 of these. We need to have a 2 to 4 decoder rather than a 1 to 2 decoder, but everything else is exactly the same. So once again, all 4 of these devices here share the same address lines. You can see them shorted together there. They also share the same control lines, but what is different here is I'm using this 1 to 2 decoder. I'm sorry, 2 to 4 decoder to turn only one of these devices on at a given time. That means the control signals for this 2 to 4 decoder effectively become the 2 most significant address bits. In this case, it's 13, 14, which is essentially bits 14 and 15 in the word here. So you can see it over here once again. So there's like 4 sets of whole bunches of 1s and bunches of 0s. So these are equivalent. The difference being is this row right here, and that is effectively assigned by the decoder output right there. Looks good. And that's how I'm going to make larger memories from smaller ones.